we have discussed, so if you have a force, you have a displacement x, and there is an angle between them. So if this angle is from 0 to 90 degree, positive work. 90 degree, 0 work. 90 degree to 180 degree, negative work. So let's look at this problem. You have a crane tower lower something. You have the work done by gravity. Okay, so pay attention. Something is going down with constant speed. Going down with constant. So the work done by gravity and the work done by tension. Which one is positive? Which one is negative? Displacement going down. Gravity. Tension. So the angle between gravity and displacement 0. 0. Cosine 0 give you 1. So gravity give you positive work. Tension and displacement opposite. So it's 180 degree. 180 degree negative 1. So it's negative. So I'll find this one is right. Let's look at another example. Now, we set up a cart on a ramp, and then we connect with a string through a pulley, and so this weight is going down, so the cart is going up. We want to know what's the work done on the cart by those three forces. Normal force, tension, gravity. So we can almost immediately find out what's the work done by normal force in this case, right? Normal force pointing in the positive y direction. This is your displacement. So what's the angle between normal force and displacement? 90 degree. Cosine 90 degree give you 0, so the work done by normal force in this case is 0. Okay, how about tension? Tension pointing in the positive x direction, displacement. So tension is in the same direction of displacement, which means this angle is 0. Good. So you have the work done by tension should be tension times displacement times cosine this angle. Now that's the work done by tension. Okay, then we need to find out what's the work done by gravity. So that's your direction of your displacement. That's your direction of gravity. So this angle, if you figure it out, so this is 90 degree, this is 90 degree plus, so this is 97 degree. Cosine 97 should give you a negative number, so gravity is doing negative work. It's easy to imagine because this card is going up, right? When it's going up, gravity is doing negative work. So you need to find out what's gravity, what's displacement, and the angle between gravity and displacement. So you find this number. So basically, you always just need to use this to calculate work done by a force, F delta x cosine theta, and theta is the angle between force and displacement. Now you'll find that the total work done on the car is positive, which means the car will have some kinetic energy in the end. Now we can derive more generally, even if the force is not constant. So we have Newton's second law, F equals m times acceleration. Now acceleration is derivative of velocity over t. So we use chain rule. So we have dvx dt is dvx dx dx dt. Now dx dt on the other hand will give you vx. So you have force is m dvx dx dvx. And you do an integration on both sides. With respect to dx, you have this equation. Now, you can, for this integration, you can take m out, integration dvx dx. Now, this is a very simple integration, right? Integration of x over x. You should have 1/2 vx squared. And you integrate from vi to vf, so you have integration of f over dx give you 1/2 mvf squared, subtract 1/2 mvi squared. So this is a more general proof of work and energy system theorem. So the total work done on an object should equal to the change of kinetic energy. So actually it's easier for us to write it this way to understand. Total work should equals to final kinetic energy, subtract initial kinetic. This is our work energy theorem, which is very important. Total work done on the object equals to final kinetic energy, subtract initial kinetic energy. Now, if you already have a changing force, the force is not constant, so we can recall what we learned. So because displacement is integration of velocity over time, right? Displacement. So if you have a velocity versus time plot, see the area under this curve will give you displacement, which is the same thing. And now your work is integration of f over x. So if you have f and x plot, then the area and it will give you work. So if you have force versus this position plot, this area will give you work. And the exact value can be obtained by integration. So in this way we can calculate this one. You have a force versus position plot. We want to find out what's the kinetic energy when the object is here. Okay, so what it tells us, the particle has 2.0 joules of kinetic energy here. So which means when the object is here at 0, it has KEI 2 joules. And we want to find the KEF here. What do we need to do? We need to use the work energy theorem. KF subtract KI equals total work done. Now total work equals this area. We calculate the area, which is 1/2 times 2 times 4 equals 4 joules. So this is 4 joules, 2 joules, so apparently this one should be 6. Okay, this is the definition of work in 3D. And well, you can understand this good, but if not, it's okay. Special case, spring force. Now we remember Hooke's law. The spring force is proportional to displacement. F equals kx, and k is spring constant. So which means you have, for spring force, you have this plot. Now the area, this is x, kx, area of a triangle is 1/2 kx times x 1/2 kx squared. So this is the work required for you to pull